have Michael James. He is a civil geotechnical engineer with 40 years of professional experience, 33 in practice, and 7 as a professor and researcher. He's got his bachelor's from Carnegie Mellon and master's from Berkeley and a PhD from Montreal. His areas of expertise include slope stabilization, dam design, numerical modeling, and seismic behavior of dams and tailings impoundments. Since 2019, Michael has been an engineer of record for Agnico Eagle mine sites in Canada and Mexico. And he will be talking about, the evaluation of nonlinear dynamic numerical simulations for TSFs.
Good morning, everyone. Sorry, my voice, I had a little bit of a cold last week, and it's not what it should be. I'm going to talk about how you evaluate the numerical reports you get for the seismic performance and stability of tailings storage facilities. Is it not working? Oh, here we go. As we all know, the mining industry is moving towards the 10,000-year recurrence interval, or the maximum credible earthquake, for the evaluation of tailings storage facilities. And currently, often we use analytical methods such as the pseudostatic method or the post-liquefaction methods. These methods are based on a limit equilibrium analysis and are very simplistic and erroneous, with the amount of error and uncertainty increasing with earthquake intensity. Now, the other option is to use numerical analysis, but those require really advanced skills, and the evaluator of these reports has to have some knowledge of what's happening so we can evaluate them in a very competent manner. Here's a small case history, the Monkey-Koshi gold mine in Japan. This was an impoundment of about 22 meters maximum height, slurry deposited tailings with a relatively high phreatic surface. It was retained by 3 dikes, dikes 1, 2, and 3, all upstream raised, compacted volcanic soils and tailings. In January 1978, there was a magnitude 7 earthquake that resulted in failure of these 2 dikes, dikes 1 and 2. Dike 1 failed during the main shock, magnitude 7. You can attribute its failure to both strength loss due to excess border pressure generation, as well as direct dynamic loading from the shaking. But dike number 2 failed hours after some aftershocks. This dike failed because the generation of excess border pressure during shaking led to dissipation that created destabilizing seepage forces. So we have 2 cases here. The dike can fail during shaking or after shaking. Okay, here are some primary static failure modes. During shaking, you have 3 that can occur due to the dynamic loading. That is the pseudostatic method with minimal strength loss. You can have actual strength loss and liquefaction leading to failure. And you can have deformation that leads to overtopping or possibly a problem with your spillway. After shaking, you can have continued deformation because of residual velocities in the model or in the tailings storage facility. That would also cause failure. You can have a loss of strength that's manifest after the end of shaking. This is what we call post-liquefaction analysis. And also you can have this excess border pressure generation that I discussed with dike number 2. And the fourth thing you can have is, if you have a high phreatic surface, the tailings are going to consolidate. So at the end of shaking, or sometime afterwards, when it consolidates, you will have a layer of water on the top of your tailings. If your perimeter dikes are not designed to retain that water or have filter protection, they could fail. Or you could have overtopping because of the deformation caused by consolidation. This is not very effective. Can you advance the slide if I can't do it? Oh, there we go. Did we go 2 slides? Or? Yes. Okay. Oh, okay. For this presentation, I created this tailings impoundment, which is the Mile High Tailings Storage Facility, a very original name. It's about 20 meters in height, slurry deposited tailings, high phreatic surface. It's closed. The tailings we consider consolidated because there's a cover on top as well. And we're going to apply the 10,000-year recurrence interval to see how it reacts. Now, dike number 1, we've got a starter dike, 10 meters high, compacted clay, sand, sandy clay. We've got 2 raises of compacted tailings that are resting on beds 2 meter thick of tailings mixed with raised rock. And dike number 1 is a monolithic rockfill structure with upstream filter and transition zone. Excuse me. Here are the seismic loadings, the design earthquake ground motion from the ASCE website for this site, which is located right here. What you see on the left is the spectral acceleration diagram for this site. And on the right, you see the disaggregation analysis. This is a combination of all the possible events from the probabilistic analysis that are used to create this spectral acceleration diagram. And the modal one, the modal magnitude pairing distance, is the one most likely to occur. That's a magnitude 5 with an epicentral distance of 5 kilometers. Now, from that, I've calculated the Arius intensity, which is a measure of the energy content of the ground motion. Basically, the energy per unit mass is going to pass through the system. And in my opinion, this is the most important parameter when you're evaluating the seismic stability of an earthquake in a numerical method. So I created an artificial ground motion, H404 here. That's in fairly good agreement with the spectral acceleration. Blue is the design, and red is the from this ground motion. There's no need for this ground motion spectral acceleration to match exactly the one from the design ground motion, because that design ground motion spectral acceleration includes all the different events that we saw in the disaggregation analysis. So if you try to match it, it will be a little bit over-conservative. And then we can see the other parameters for this ground motion. We see the PGA, the Arius intensity, which is within the range we expect, as well as the duration. This is typical for the east or central coast of East Coast or central of North America, and that's a high-frequency event. On the West Coast, they'd be much more lower frequency. Now, for this modeling, you have to pick your models, your material models of behavior. What I used here is for all the materials that did not exhibit or would not exhibit excess pore water pressure generation or liquefaction, more Coulomb model. But for the tailings, both compacted and retained, I used the UBC sand model, which can simulate pore water pressure generation and liquefaction. For the bedrock, I used an elastic model because I don't expect there to be any risk of failure there. And then I applied this global damping to the model, this Rayleigh stiffness damping. The point there is when you enter an acceleration on the bottom of the model, the acceleration you get out of the top of the rock should be exactly the same. If you get a different acceleration pattern at the top of the rock, your tailings facility is not seeing the design earthquake, it's seeing something else. So this is the first point of verification, to verify the acceleration that goes into the bedrock is the same that comes out of the bedrock. If the surface of the bedrock is uneven, you've got to verify that at different locations. And there you see the damping parameters used for the more Coulomb materials. The UBC sand model can be calibrated. You can take a cyclic direct simple shear tests, and you can simulate them numerically to make sure that for this material, you have the parameters that match what you saw in the laboratory in terms of border pressure generation and shear strain, and also in terms of number of cycles of trigger liquefaction. And here we found a quite good agreement between the laboratory and the model. So calibration is quite important. Now, here are some of the results. Upper left-hand corner, you see the site response. This is what's happening between the bedrock on the bottom where we input the acceleration and on the top. They're exactly the same, which means this is correct. This means the impoundment's going to see the correct ground motion and energy. Now, on the bottom, you see for the left dike 1, for the right dike 2. We see the accelerations horizontal on the bottom of the rock and on the crest of the dike. And we see significant amplification on both cases. Now, this is expected, and this is something we can verify, because when you have an embankment or a dike and you shake it, an earthquake shaking, the energy of that ground motion is focused towards the crest, and you get an amplification of 1.5 to 2.5 times what you from the bottom to the top. And if you don't see this, there's something wrong with your damping parameters or your materials. Now, the effect on the left is a little bit chaotic. That's because dike 1 has those raises. And because it has those raises, it's affected both by the structure of the dike itself and by interaction with the impoundment. So that level of chaos you see in the accelerations for dike 1 is expected. And for dike 2, this is expected. So another point of verification. Now let's look at the response right in the middle of the tailings at mid-height. Here we see the accelerations, top of rock in the middle of the tailings, and we see there's some amplification, particularly at the beginning of the ground motion, a little bit less towards the end. And the second graph is the cyclic stress ratio, the ratio of the applied shear stress from the earthquake to the initial effective vertical stress. What you can see there is you see those amplitudes of shear stress about 0.5, 0.1. This is where you're going to start seeing pore water pressure generation. And by looking at the number of cycles, you can pretty much say that you're going to have liquefaction here. You'd expect liquefaction here. You could actually take Seed's chart, look at these number of cycles, take a magnitude, and calculate the risk of liquefaction, and it would be fairly accurate. At the bottom, you see the excess pore water pressure ratio at 3 heights, quarter height, mid height, and 3/4 height in the model. And it shows that by the 6 seconds of shaking, there's significant pore water pressure generation, liquefaction in the middle and upper part of the tailings, but not in the lower part of the tailings. And this agrees with what we see in the cyclic stress ratio. Okay, it's important to look at what happens at the end of shaking. Here, at the end of shaking, we see the contours of excess pore water pressure ratio. And they confirm what we saw in the previous graphs where we have liquefaction in the central and upper part of the impoundment. But if you look under the races of Dike 1, there is no liquefaction, at least not right under the races. And that's because the initial static shear stresses applied by the dikes are preventing reversal of the shear stress, which inhibits pore water pressure generation. This is an effect that would diminish with increasing earthquake intensity. So it's not something you can rely on for large earthquakes. On Dike 1, in that area, you see a little bit of difference in the pore water pressure response, and that's because of the interaction between Dike 1 and the tailings because they have different natural frequencies. The lower graphic is the horizontal displacement in centimeters. You see the raises of Dike 1 in white. The raises of Dike 1 have moved about 15 centimeters downstream. Dike 1 hasn't moved, and that makes sense because it's a compacted rockfill structure, and you should not expect to see displacement. The tailings have moved towards the center because the surface of the impoundment was sloped at 1% from the edges to the center. So when you do a numerical analysis, how do you decide if you have failure or not? You have to look at the pattern of displacements and velocities at the end of shaking, like in some of the graphs that were shown, and use your judgment to decide, is this equivalent to failure? What's my criteria for failure? Is it physical failure of the system or a certain amount of displacement that will interfere with, say, a thin filter, a connection, or a spillway? You can also look at the pattern of velocities to see if things are still moving at the end of shaking. But then again, you have to look at the conditions at the end of shaking to see what's going to happen next. Is the system still moving? Have pore water pressures generated to a point where they can dissipate and cause a problem with respect to stability? Or is there potential for a problem with the consolidation? For this impoundment, I found that it's stable under the ground motion. So I took the same impoundment and I multiplied the ground motion by 5, a much larger earthquake. And I ran it, and after about 9.5 seconds, it stopped because some elements were excessively deformed or distorted. So I went back to 9 seconds to see what was going on, and here you can see 2.5 meters of displacement at Dike 1 in the downstream direction, but Dike 2 is still stable. Look at the velocity vectors. These are the velocities of the individual nodes of the vectors. What you see at Dike 1, races 1 and 2 are moving downstream at the rate of 3 to 5 meters per second. This indicates failure. This is a clear indication of failure during shaking. So some basic considerations. First, when you do this type of analysis, you have to know, what am I modeling? Am I modeling the current state, the future state, or some state well after closure? So take that into consideration. What is your failure criteria? Is it a certain displacement that'll disturb your spillway? Is it actual physical failure of the system? You need to set those criteria and stick to them. Your material properties have to match your life cycle because there's consolidation and aging that occur. Before you start the dynamic analysis, you have to confirm static conditions. Are the stresses and pore water pressures what you expect for that phase in the life cycle? That's a very important point because if that's not right, your dynamic loading, your dynamics analysis is not correct. Ground motion records. You've got to run maybe 5, 7 ground motion records based on the design earthquake ground motion, just to make sure you're seeing the different things that could happen due to different frequency content to the ground motions. You don't have to exactly match the spectrum as I mentioned, but you should match certain parts of it. And you should really check the area's intensity to make sure that it's something that's reasonable, because as I mentioned, that's what really is going to control whether you have failure or not. You have to look at your materials and what are the behaviors you're trying to simulate. Is it strain weakening, liquefaction, cyclic mobility? What are the issues of concern? For example, if I had a very large rockfill dam, very high, I would use probably a hyperbolic model for the rockfill that incorporate the rockfill behavior in a more realistic manner. You've got to verify the transmission of ground motions through the system, through the bedrock first of all, to make sure that's correct, and then through different parts of the system to make sure that it's being faithfully transmitted, or reasonably transmitted, I should say. You should plot the accelerations, the cyclic stress ratio, and the excess border pressure ratio at key locations, just to make sure that they're reasonable. I've shown a few locations in a real model. I'd be showing much more locations, just to confirm what's happening. And then, as I showed here, different conditions at the end of shaking, pore water pressure ratios, displacements, horizontal, vertical, velocities, just to understand what are the conditions when shaking stops, and is there a risk that something will happen afterwards? If you see a risk that something will happen, you have to identify what is that risk. Is it continued displacement? Is it pore water pressure dissipation? Is it consolidation? If that's the case, you've got to do a post-shaking analysis. And a post-shaking analysis, usually you have to do it with different models or modify the model you have, because most liquefaction models do not model post-shaking behavior in terms of the elastic moduli or pore pressure behavior. So modify the model and then do your post-shaking analysis if necessary and make another assessment as to whether it's going to be stable or not stable. I think that's going to end my presentation. Thank you very much. Oh, sorry. Can I put out one more thing that I forgot? If I go back here, yes, here. Look at the frequency content of the accelerations. Very high frequency, right? What about the frequency content of the shear stress? If this was a West Coast earthquake, they'd have pretty much the same frequency content. Here it's different because the individual cycles, amplitudes of acceleration aren't enough to change the direction of the shear stress. So the question is, will this impoundment respond to the frequency of the accelerations or the shear stress? I think it's more likely to respond to the frequency of the shear stress, so maybe we should be looking at velocity spectrum instead of acceleration spectrum for the East Coast and the center of North America. Thank you.
All right, we do have a little time for questions. I'm not seeing any in the app, so any hands up? All right. Sitting in the front of the room to a microphone, sorry.
Hey, James, thank you for the presentation. Awesome. I'm a little confused. I didn't follow in the beginning. Can you go back? Which one failed first and which one failed after shaking?
Oh,
If you show
dike
on the
number
section.
1 at Mukikoshi,
Failed first.
yes, during shaking, and dike number 2 failed after shaking due to excess border pressure generation.
In what? In the embankment or?
It was an upstream raise, so it failed. What happens
But
is the
two
excess,
was a rock fill, right?
oh, sorry, this one was, sorry, this is case history. This is
Yes.
not rockfill. This is compacted.
Okay,
This is compacted volcanic soil and tailings.
okay.
So the border pressures generated underneath the raises, dissipated between the raises, and they stabilized it because you had a seepage force that in the outward direction.
Oh, I'm with you. Because in the model, it looks like one is a solid structure, right?
Oh, this isn't what I'm modeling.
Oh,
Sorry.
sorry. Was it just me confused or anyone else? Sorry.
Sorry.
All right, we have time for one more quick one.
Do you know a site that doesn't have a dike 1?
Thank you very much. I would like to just a question about the graph that you show us. And I would expect, in my mind, the ratio of pore pressure higher on the bottom, not on the top. I would like to understand why it's happening, if you could help
Why
us
it's
to
less
understand.
at the bottom?
Yes, no, because could you put in the graph with the ratio?
With the pore water pressure and
Maybe I can try explain you. I would expect that the higher one, near one,
I'm sorry, this
on the
thing just doesn't
bottom.
work. Oh, there we go. Here, right?
No, the next.
Next?
I think the next. Yes, exactly this one. I would expect when we look at this, we're in the top of the tailings. we can see the ratio near 1. So in my mind, it's seeing that we have a higher pressure generation with stress variation. And I would expect this red one on the bottom. And I couldn't understand what's happening, and I would like to understand what's happening.
The bottom
this.
right of the impounded tailings, you mean?
Yes, on the bottom of the tailings field.
Okay,
Not on the top. Look, the red one is on the top. I would expect it on the bottom.
the red one on the right side, right? Your dike 2?
Yes.
Okay, what's happening is you have a dike of rigid compacted rock next to tailings that are soft, and they're getting softer as excess border pressure generates, and they're not in the same frequency. The dike's gonna be much higher frequency than the tailings because they're softer. So you're gonna have like a pancake effect, it's gonna create more border pressure close to dike number 1. Why it's, okay, sorry. Border pressure, assuming that the corrected penetration resistance is uniform, border pressure always starts from the top and works its way down. And part of that reason is because if we look at the stress profile, the vertical stress, you have higher stress, which means you have a lower CSR.
All right, thank you.
No, you're welcome.
Great questions.